Hello, warm welcome to the second session on applications of forces for year 13. We've had a look at 7.1, we've introduced some ideas. Now it's time to go forward and have a look at some forces acting on inclines. Still, these surfaces are going to be modelled as smooth. Next lesson we'll look what happens if the surfaces are modelled as being rough, where there's friction. So before we get started with the main examples, here's a couple of throwback worked examples for you to have a go at. So I'll call them warm-ups as I always do, but I will show you how to do them after. So try these independently, freeze the video here, do your best, and then after you've tried them, press play, and I'll show you how I might tackle them if I were in an exam situation faced with these myself. Alright then, so let's have a look together at warm-up 1. So here, you have two forces, P and Q, acting on a particle. The force P has magnitude 7 and is acting due north. In terms of the diagram, due north we can just say is being straight up. The resultant of P and Q together is a force of magnitude 10 newtons acting in a direction with a bearing of 120. Find the magnitude of Q. Well, there's actually two main ways of doing this. So one way, the way I'd suggest is more versatile generally, is resolving forces. So the first method I want to have a look at is if we resolve components and then use vector addition or subtraction. So first of all, I'd suggest we might have to draw out a force diagram, thinking about where P, Q and R would be. So we're told about P. So P, it says, has magnitude 7, and do that in green actually. So P has magnitude 7 and is acting due north. So I'm going to draw in P first of all. So that's P, magnitude 7, like so. So that's P. We're also told about this resultant. So the resultant I'm going to draw in red. The resultant of these forces is a force of 10 newtons and acts in a direction with bearing 120. So if we label this on now, we should see that it's going to be a line which is a bit longer than this P, obviously, and it's going to be acting slightly downwards because of its bearing of 120. So it's going to be looking something like this. So I'll label on that this is R. I'll also label on that this is going to be magnitude 10. And if the bearing is 120, this means that from here to here will be an angle of 120. So we can just use a fact of this bearing of 120 for this resultant force. So because resultant is the sum of P and Q, and that means that when we use vector addition, of course, the vector we're adding on goes at the arrow end of the vector we're adding it to. So Q would start here, the arrow end of P, and must therefore go down to where R finishes. So R is along P and down Q like so. So this is Q we've got. So we can now use this idea of a vector addition. I'll mention a different way of doing this after. You can see already it's a triangle, so we might be able to use something else. I'll come to that in the second method. So R for resultant is what you get if we add together vector P to vector Q. This is going back to year 12 ideas. So what we could do here is express P and R as unit vector forms. And so P, because it's just going straight up, we can say that P is just simply 7J, where J is the component going in the positive Y direction. Now R, because R's on this angle here, what we can do is we can section this out into an acute angle. So if I just draw an acute angle here, we can work out quite easily what this is. So if I highlight this in green, for bearings 120, this bit here is a right angle, so it means it goes on a further 30 degrees below the positive x-axis. So this angle here is 30. Then, knowing that, we can resolve r into a vertical component and a horizontal component. And so the horizontal component of r, so r going along this way, and the vertical goes slightly down. We need to remember that the vertical components is going to be the magnitude of the force, in this case just r, which is 10. In fact, I'll just call it 10, why not? So that's going to be 10 sine of the angle, so that's 10 sine 30. And the component of r going horizontally along will be 10 cosine 30, like so. So we can have this information in. So r is going to be 10 cos 30 units along in the positive x direction, in the I direction, so it's going to be 10 cos 30 I, and because it's going down, it'll be minus 10 sine 30 in the positive y direction. Now this can be simplified because cosine and sine of 30 are exact values. Feel free to use a calculator regardless. So 10 cosine 30 gives 5 root 3, so that's 5 root 3i. And then sine 30 is going to be 0.5. Again though, feel free to be my guest. Use this on a calculator. 10 sine 30 gives you 5. So that's then minus 5j. So we can now take this and rearrange to find out what q would be. So q will be vector r minus vector p. And so if we just subtract p from both sides. So r is 5 root 3i minus 5j. Then if I subtract p again, I'm subtracting a further 7j. So this gives, say that's I, apologies, that's I. So we have 5 root 3i minus 12j. Just make sure I'm not going to get in the way of my answer for part 2, like so. So now we've got the I component and the j component. We can now work out the magnitude of q. So therefore the magnitude of q will be the I component squared plus the j component squared, and all of that square rooted. So if we just do this on the calculator, we'll get there. So the square root of 5 root 3 squared plus the square root of minus 12 squared, which will just be the same as 12 squared, which is 144, but put it in like this if you wish. Root 219 as a more exact, as a decimal answer I should say, that gives us 14.8. So 14.8 newtons. We can now think about part 2. So now we need to think about the direction of q, giving the answer as a bearing. So q is this blue line angling downwards. So if I just redraw it down here, like so, we can add in what we found out about it in terms of I and j components. So we worked out the I component and the j component. So if this is q going down, I can make up this angle here, let's call it theta. So going along in the I direction, we had 5 root 3i, and then going downwards, we had 12. So now we know the opposite side, which is 12, and the adjacent, which is 5 root 3. So we can work out theta by using tan minus 1. So theta equals tan minus 1, opposite, divide by the adjacent. So if we now do this, so shift tan minus 1, 12 over 5 root 3, we get 54.2 degrees to three significant figures. Now that's not the bearing, we want the answer as a bearing, so therefore the bearing of Q, then bearings are always measured from north. So what we want here, the bearing of Q is all of this, so it's theta which we just worked out, plus this 90 degree angle. So 90 plus theta, so 90 plus 54.2 to three significant figures, that gives us a bearing of 144 degrees. So that's one method for doing question 1. Let's now have a look at a second method using the idea of a force triangle, and then we can also do the cosine rule and the sine rule for part 1 and part 2 respectively. So we could construct a force triangle, then use the sine and cosine rules. So going back to the triangle we started with before we carried through the calculations, we had this triangle here, just to remind you. So that's P, which is 7. This is 10, which is the resultant, and we need to find the magnitude of Q. Now what we were told as well is the direction that the resultant is acting in was 120 degrees, a bearing of that. Bearings are measured from north, so we can start from this line here, which is P, add this on, and that's 120 degrees, as hopefully you can see fairly straightforwardly. We know two sides and the angle in between. This is now a green light to use for cosine rule. So just remember, we can find sides using the cosine rule by the general rule here, where a squared is b squared plus c squared minus 2 times b times c in any order, multiplied by cos of the angle opposite to what we want to find. So in our case, the side and the angle known relate to Q and the angle opposite to Q, which is 120. So if we replace A with Q and B and C in any order with 7 and 10, we can say that the magnitude of Q, square rooting all sides, so B I'll call 7, C as 10. So the magnitude of Q will be 7 squared plus 10 squared minus 2 lots of 7 times 10 multiplied by the cosine of this angle 120. So if we now just bang this into the calculator, square root 7 squared plus 10 squared minus 2 times 7 times 10 times cos 120, we get exactly the same solution which you would expect, so 14.8 newtons. So I'm going to leave that in my calculator, in fact, so we can substitute in that magnitude of Q with what the magnitude of Q actually is. So the magnitude of Q is about 14.7986. Now for part 2 here, it says to find the direction of Q, giving your answer as a bearing. So what we can do here is use the information we've already got from this first question and apply it here to this diagram. So if I just scroll this down, now we want this as a bearing, of course, so bearings are measured from north. So if I just extend this line up further, we want the bearing, so we want to work out this angle here, and we can relate that to the bearing. So if I just add on this, we want to find the bearing which should be that. First of all, we can find out this angle and subtract it from 180, then we'll have the bearing. So if I call this angle, I don't know, I'll call this alpha. Why not? We can now use the sine rule. And we know we can do that because we know the side opposite to the angle we want to find, and we also know an angle-side pair based on what we found out from part 1. So, sine alpha divided by the side opposite to it, which we know is 10, that'll equal sine of 120 divided by the size of the side opposite to it, which we worked out previously, magnitude Q, which was 14.8. Well, more accurately was 14.7986, and so on. So what we can do here, we can multiply both sides by 10 and then do inverse sine. So alpha is going to be sine minus 1 of 10 sine 120 divided by 14.7986 blah blah blah. Now this answer is already stored on the calculator, so we can leave it there so the calculator maintains all the accuracy for us. So look, the answer should be there. So if I just do shift sine minus 1, 10 sine 120 divided by the previous answer stored, we get 35.8 degrees. So worked out alpha here, which is 35.8. Therefore, the bearing of Q which is this angle here I've just highlighted in this purple colour. Using the fact that angles on a straight line, on this north line for example, add up to 180, we can just do 180 minus alpha. So 180 minus 35.8, that'll give us to three significant figures, 144 degrees. Like we had before, using the previous method. So quite a long initial warm-up question, because I've shown you two different methods, and it was a fairly involved question for quite a few marks back in the day, that one. But there we have it. Let's now have a look at warm-up question 2. So here we have a fairly standard, although not too straightforward, pulley question. So we've got two particles of mass 3 kilograms and m kilograms, where m is less than 3. They're attached to the ends of a light inextensible string. The string passes over a smooth fixed pulley, this circular thing here. Particles are held in position with the string taut and the hanging parts of the string vertical as shown in the diagram. The particles are then released. The initial acceleration of each particle has magnitude 3/7 g. So let's add on the information we've been told. So the initial acceleration was 3/7 g. So let's think about which direction the acceleration is going to go in. Well, m is the lighter particle. This is the heavier one. So therefore the acceleration is going to be down on that side, and this one's going to be whizzing up, because this particle is going to be pulled down by this heavier one. The magnitude is 3/7 g. So g is 9.8, so we need to work out 3/7 of 9.8. That's 21/5, which is 4.2. So the acceleration is 4.2. I think by putting it as 4.2, it looks a bit less alien. You could leave it as terms of 3/7 g. I choose to do it this way, either or. So here there'll be a force which relates to the weight of this particle. So because that's 3 kilograms, then if I just change these here to a circle, then the weight of that one will be 3g. The weight of this one will be the mass of it times g, which will just be mg. Tension always acts away from an object, so relative to this one here, the tension will be acting up. This one here, the tension, which will be the same, will also be acting up. So we can now think about how to tackle this in terms of thinking about this particle here or that particle over here. So let's consider the 3 kilogram force, because that's the force, so that's the particle we know more information about. We know the weight and mass of this one, we don't know the mass of this one. So for the 3 kilogram particle, what do we have? Well, we can apply F equals ma to the 3 kilogram particle, so let's do that. So the resultant force up will be negative because the particle is going down. So let's take down to be the positive direction. So take down to be positive because that's the way the acceleration is going to be. So the net force acting down will be the 3g weight minus t, because t is acting in a direction opposite to the overall acceleration. So this is the overall force acting downwards. By F equals ma, that will equal the mass of a particle, which is 3, multiplied by the acceleration of the particle, which we know is 4.2. We can then rearrange this quite easily, so therefore t will be 3g minus 3 multiplied by 3 times 4.2. So if we just get this and calculate it, 3 times 9.8 minus 3 times 4.2, we get 16.8. And so the tension is 16.8 newtons. And for B, the value of m, we can now consider the second particle. So for the mass m, again we can apply F equals ma. So because for this particle m, the acceleration is going up, we can take this time up to be positive on this side. We can change from one question to the other as long as we're consistent within each question, or question part. So for question part B, let's have up as being positive. So the overall force acting upwards in the direction of acceleration for m is t minus mg. And that will then be equal to the mass of it multiplied by the acceleration. So mass is m, acceleration is 4.2. So m multiplied by 4.2 we can write as 4.2m. We also know the tension, which is 16.8, so we can fill that in. And add mg to both sides gives 4.2m. G, of course, is 9.8, so let's call that plus 9.8m. And if we add those together, 4.2 added to 9.8, that gives us 14m. So therefore the mass will be 16.8 divided by 14, and that gives us a value of 1.2. So the mass of the second particle, the value of m, is 1.2 kilograms. And we're done. We can now have a look at some examples based on what we're looking at today, which is statics involving smooth particles and smooth surfaces. So worked example 1, modelling with statics. We've got a smooth bead Y at the bottom of this diagram, and it's threaded through on a light and extensible string. And so the string is attached at 2 points X and Z on the same horizontal level. If we're talking about strings, we should know almost as second nature by now if there's going to be an associated tension. So the tension can be modelled as being the same on this part of the string and that part of the string. And because it's a smooth bead, that is, because it's a smooth bead, the tension will be consistent on both sides. So what we can do now as well, because we've got this problematic tension acting at an angle, I'd suggest we go back to some GCSE angle facts and remember about alternate angles, as I used to call them Z angles. So if this angle here is 30, we can say that this angle here will be 30 as well. And what that will enable us to do will be to resolve this second tension in terms of this angle 30, so we can get the tension here into horizontal and vertical components. So therefore for this one, the tension going adjacent and opposite like that, going opposite would just be T, the magnitude here, multiplied by sine of the angle, so T sine 30 going up. Going along will be T cosine of the angle, T cos 30. So we need to find the tension in the string and also the weight of the bead. So if we just consider forces going horizontally, and because it's an equilibrium, the sum of the forces going in the horizontal direction will be equal to 0, they'll balance. So forces going to the left will be the same as the forces acting to the right. So if any force is acting horizontally to the left is this 8 Newton force, so that must be equal and opposite to this T cos 30, which is the only force acting to the right. So if we just divide both sides by cos 30, T must be 8 over cos 30. So if we just work out what this is now, 8 over cosine of 30, that's going to give us a value of 16 root 3 over 3, which equates to 9.24 newtons to 3 sig figs. We now need to work out the weight of the bead. Now, not the mass, but the weight. So now we need to factor in forces going up and down. Because it's an equilibrium, the forces going up and down will be equal to 0. And there's one force acting in the up-down direction we've not considered, which is the very force we're trying to find out, which is the weight of the bead, which is mg. Now be careful here, most time a question will ask you to find the mass. We here want to find the weight, so we just need to find mg. Don't divide by g to find m, that would be a mistake. Just find and isolate mg. We can do this by considering forces going up and down. So the total of the forces or components acting up will be equal and opposite to the total of the forces acting down. So acting up, we have T plus T cosine 30. However, we know what T is now. We know that T has a value of 9.24 newtons. So we can fill this in. So acting in the up direction, we've got T, which is about 9.24 newtons. Also got T sine 30, which is 9.2 sine 30. And that is going to be equal and opposite to the weight of the bead, which is mg. So actually all we need to do now is just to work out what 9.24 plus 9.24 sine 30 is. So therefore mg will equal, and if I look on our calculator display, we've got the exact value of the tension stored. So let's leave it there in exact form so we don't fall foul of any rounding error. So leave that as our 9.24. So 9.24, that answer, plus 9.24-ish, which is our stored answer, multiplied by sine 30. That gives us a value of the weight as 8 root 3, which is to 3 significant figures, approximately 13.9 newtons. So the weight, because weight is a force, we give it in terms of newtons, so the weight is 13.9 newtons. And that's the first worked example completed. So let's have a look now at worked example 2. For worked example 2, we've got quite a lot to sort out here. So you can tell this by a big block of information, about a paragraph's worth. So let's just absorb, digest this and add it to the diagram. First of all, we've got a mass of 3 kilograms, which is here. Let's add that straight away to the diagram. If its mass is 3 kilograms, its weight is going to be 3g. So let's add this on. Weight going down of 3g. What else do we need to add? So reading on. It's a smooth plane, so again no friction. It's inclined at an angle of 45 degrees to horizontal, which has been given. The mass is attached to a cable which passes up the plane along the line of greatest slope and then passes over a smooth pulley at the top of the plane, so this pulley's here. The cable carries a mass of 1 kilograms, which has been freely supported at the other end. So this mass here on the other side is 1 kilogram. So its weight is going to be its mass multiplied by g, but because its weight is exactly, so its mass is exactly 1 kilogram, its weight will be 1g, which we can just leave as g. We also need to label on this force, which is the tension, which is within the string. Now we are told as well about this pulley that it's smooth, so the tension will be the same on the string either side of this pulley. Tension always acts away from the object in question, so relative to this weight here, tension will act upwards. Relative to this one here, tension will act diagonally upwards on this string. So P here, as you can see, is acting at an angle. So what we may want to do, as normal in fact, is resolve perpendicularly to the slope and parallel to the slope. So here what we need to do is take both the weight and P and resolve perpendicular and parallel to the slope in question. So first of all we can do this for the weight. So let's just do this first of all. So the weight of this particle here I'll do in a red colour because, well, why not? So the weight I'll do in a red colour. So it's going to go down parallel like so, and similarly for this P force I can do this both parallel and perpendicular to the slope as well. And so I can do it acting downwards, then consider it acting like so. For the weight, we need to work out this angle here. Well, we do and we don't. We need to remember that if this angle here is 45, this will be 45 here. Therefore, the component of the weight acting parallel to the slope, this opposite component to this angle, will be the magnitude of the hypotenuse, which is this black line 3g, multiplied by sine of the angle, so that's 3g sine 45. The perpendicular component, the adjacent component to this angle, will be hypotenuse cosine 45. Likewise here, if this is 45 degrees, we can use GCSE Z angles to realise that this must be 45 as well. If you're thinking, what's he talking about a Z angle for? Where's this Z? Well, if this is 45 and P is acting horizontally, then that's the Z I'm talking about. That's 45, so this is 45 as well. We can use the same idea to resolve P. So the component which is going to be opposite to the angle is hypotenuse sine of the angle, so P sine 45 that way, and the component acting along the slope will be P cos of the angle, so that's P cos 45 acting up. Just one more force we've not considered, which we may as well label on. We also need to label on the normal reaction. Normal reaction always acts perpendicular and away from the surface, so the normal reaction will act in this direction here. I'll just call that N for now. That's enough labelling to start with, so let's just think about what we're being asked to do. We need to find the magnitude of P. So what we can do here is one of a few things. What I'd suggest we do is we use what we've resolved already. So let's think about forces acting parallel to the slope. So for A, forces on the 3 kilogram weight acting parallel to the slope. Can't spell slope, that's going to be, what am I doing? Slope. S-L-O-P-E, wake up. Forces on 3 kilogram particle going parallel to the slope. So we are told again that this is in a equilibrium system. So the sum of the forces parallel to the slope will equal 0. Another way of thinking about this is they'll balance. So going up the slope will equal the forces or components going down the slope. So going up the slope, we've got T. Also got this component of P, the P cos 45. So T plus P cos 45, that's going to equal the forces going down, and the force going down is going to be 3g sine 45. At this point, it's probably crossing your mind that we're going to be stuck because we have two unknowns. We don't know T and we don't know P. However, and if you thought this already, well done. If you look at this particle here, this 1 kilogram particle gives us a massive clue. So the 1 kilogram particle, this here, is also in equilibrium. So the total of the forces acting either up or down will be equal to 0. In other words, the tension must be equal and opposite to G. So the tension is G. And we can use that to our advantage. We can plug in that the tension is equal to G. So it all combines to help us with this whole problem. So if I rearrange, P cos 45 equals 3g sine 45 minus t, if I subtract t from both sides. But because t is g, I can think of that as just subtracting g, because t is g. Therefore, in one step, we'll have it. If we divide both sides of this equation now by cos 45, we will have worked out the magnitude of P. So therefore, P is going to be 3g sine 45 minus g, all divided by cos 45. So if we just type this in carefully on the calculator, we'll be absolutely fine. 3 times g, which is 9.8, multiplied by sine 45, minus g, which is 9.8, divided by the cosine of 45. That's going to give us a value of 15.5 newtons to 3 significant figures. Now think about part B. So the normal reaction between the mass and the plane. So again, because the system's in equilibrium, for the 3 kilogram particle again, we can say that the sum of the forces in any given direction will be equal to 0. This time we can consider forces acting perpendicular to the plane, going diagonally up and left, and going diagonally down and to the right. So the sum of the forces in this direction will equal to 0. Or we can think about them as being balanced. So the sum of the forces going in this up direction is obviously just for normal force. So that must be equal and opposite, must be perfectly balanced with all the forces acting downwards. Acting downwards into the slope perpendicularly of a p sine 45 force. So that's p sine 45. And as well, the 3g cos 45 force, the component of a weight perpendicular to the slope. So just remember to sub p equals 15.5 from part A. So sub in the value of p from A. That'll tell us what n is. So p is 15.5. Now that's stored in our calculator, so let's just leave that there. If I press A and S, it's given it to me. So p sine 45 is A and S sine 45. Then plus 3g cos 45 is just as it is. So 3 times 9.8 times cosine of 45. That gives us a value to three significant figures of 31.8 newtons. So n is 31.8 newtons. One more, just part C. State how we've used the assumption that the pulley is smooth in these calculations. Well, that's a one marker, and because it's smooth, the string can be considered as just one item, just one homogeneous string on that side and that side. So the pulley is not affecting the tension on either side. So the tension of the string will be consistent either side of the pulley. So because it's smooth, the tension in the string is going to be equal. I could say equal in magnitude, I suppose. So it's equal in magnitude at either side of a pulley. And that's all we need to say really for part C. So we can now have a look now at the last question, which was a past paper question from way back in the day, more than 15 years ago. And it's here, question 3. So you've got a particle P, mass 6 kilograms, lying on the surface of a smooth plane. The plane is inclined at an angle of 30 degrees to the horizontal as shown. The particle is held in equilibrium by a force of magnitude 49 newtons, acting at an angle theta to the plane as shown in the diagram. The force acts in a vertical plane through a line of greatest slope of the plane. Show that cos theta equals 3/5. So what we need to do here is to do some resolving. So what I'd suggest here is to add in as much information as we can. Mass of 6 kilograms, that means its weight is 6g. Next we need to resolve both perpendicular and parallel to the plane. So we need to go perpendicular and parallel like so. And we need to do the same for the 49 Newton force as well. So if I think of this as going perpendicular to the plane, sort of in this direction, as like so, and then also parallel. You'll have this sort of effect. So this angle here is theta, and we know the magnitude of this force is 49. So the component acting downwards perpendicular into the slope will be 49 multiplied by sine theta. So I'll change the colour of that so it's in the same nice blue. And the component going along the slope and up the slope will be 49 times cosine of theta. Similar to the weight, if this is 30, we need to now know and be confident with the idea that this will be the same angle here, which is 30. So this component going down the slope will be 6g sine 30. The component going adjacent or perpendicularly down relative to the slope will be 6g cosine 30. So we need to show that cosine 30 is 3/5, and so cosine 30 is used in this component. So let's just consider forces going parallel to the slope. Because it's in equilibrium, the forces going up will equal the forces going down. The sum of the forces in this direction is 0. Forces down equal forces going up. So going up the slope, we've got 49 cos theta. That must be equal and opposite to 6g sine 30, which is acting down. Therefore, if we isolate cos theta by dividing both sides by 49, we get 6g sine 30 over 49. So let this do the hard work for us. So 6 times g, which is 9.8, multiplied by sine of 30, all of which is divided by 49. That's going to give us a value as required as 3/5. But before we go on, I'm just going to mention that we can now work out what theta is. So based off this, because this can help us for part B and part C. So cos theta is 3/5, like we said. We can think of this in terms of a triangle. So if this is theta, cos is defined by the adjacent divided by the hypotenuse. So the adjacent being 3 and the hypotenuse being 5, that would give us a cosine of this as being 3/5. Now this is also, as you can hopefully spot, a Pythagorean triple. If that's 3 and that's 5, this side would have to be 4, because 3 squared plus 4 squared gives 5 squared. So although we've worked out cos theta, we've also as well worked out what sine theta is. So cos theta is 3/5. Sine theta would therefore be opposite over adjacent, which is 4/5. So that's worth just bearing in mind for maybe part B and part C, which we'll look at now. For part B, we need to find the normal reaction between P and the plane. So it's worth just remembering what we labelled in terms of our resolving earlier on from part A. So here's what we resolved for part A. One thing we didn't add in was this normal reaction. So let's just add this in now, because obviously we need to work this out. So the normal reaction will be going up and away like so. That's going to be the normal reaction. So for part B, finding this normal reaction, then we need to think about forces going perpendicular to the slope. So the sum of forces going in this direction will be balanced. So based off this, for forces going downwards perpendicularly to the slope, we've got 49 sine theta and we've also got 6g cos 30. That's going to be what will balance against n. Like I said from part A, because we worked out what cos theta was, we can also work out what sine theta was. So just a reminder from part A, over here again, we can say that sine theta is 4/5. So if we just plug this in to n, this expression for n, we can work it out. So if we just substitute in that sine theta is 4/5 in this, we've got n. In other words, n is going to be 49 times sine theta, which is 4/5. So 49 lots of 4/5, plus 6 times g, 9.8 times the cosine of 30. We've got here 90.1 newtons, and that's what n will be. To three significant figures, n is 90.1 newtons. Finally now, for part C, we're now told the direction of the force of magnitude 49 newtons is now changed. So apparently, it's now applied horizontally to P, so that P moves up the plane. The force again acts in a vertical plane through the line of greatest slope of the plane. Find the initial acceleration of P. So this 49 Newton force now is not acting downwards, it's acting horizontally. So what we can do here is just adapt what we've got here in this diagram so that it makes sense. So it's not acting at theta degrees anymore either. It's going to be acting perpendicular, so it's going to be going into P like so. It didn't say anywhere in this question that the magnitude's changed, so we can still assume the magnitude's going to be 49 newtons. We're still going to have this normal reaction and all the rest of it. But now what we can do is we can apply here, again, a GCSE angle fact. So we can still resolve 49 degrees, but we can now resolve it relative to this 30-degree angle. I'll explain why this is. So if we think about forces going down into a slope like so, and forces going along, then we can use this idea of GCSE Z angles. That's 30 degrees. That's parallel to that line. So hopefully you can see this makes a Z. So if this is 30, this angle here is going to be 30 as well. Because we want to find the acceleration of P, it's going to be accelerating up the slope like so. It's good to have in mind we need to resolve parallel to the slope. So on that note, going into the slope is this component opposite to this 30-degree angle. This component will be hypotenuse sine 30. Going up the slope, we're going to have 49 cos 30. That's a bit of a mess, hold on, that's going to annoy me. Sorry, 49 cos 30. That's clearer. We've got the weight to consider, because the weight will also have a component which is going to be going parallel to the slope. So that will have a component affecting the acceleration. So its weight was 6g. So again, in the same way resolving like we did before for part A, we can say that the weight going down will have this component perpendicular into the slope. So the component going opposite down the slope will be 6g sine 30. Again, needing to know this is 30, but this should be something you've got practice with now. And for completion going perpendicularly downwards relative to the slope, 3g, cosine 30. So we now need to find the acceleration of P. The acceleration is going to be going up the plane and parallel to this slope. So let's just consider forces acting parallel to the slope. Forces parallel to slope. So the overall resultant force, the sum of the forces going up, that's going to be 4g cosine 30 acting up the slope. And then we need to subtract forces acting down the slope, which is just 6g sine 30. And that's what this gives us. So 49 cosine 30. minus 6 times 9.8 times sine 30. That gives us approximately 13.0, but let's leave it in exact form on the calculator. So 13.03 with a few dots after, just to denote that I'm aware that's not the exact answer, nor is it our final answer. Never round too soon. Never give yourself a chance to be vulnerable to any rounding error. Only round at the very end. So we can now apply F equals ma. So the sum of the forces going up the slope, we now know equate to about 13.03. So 13.03, etc., equals the mass of the particle, which is 6, multiplied by the acceleration we wish to find. So therefore the acceleration of this particle up the slope will be 13.03, and so on and so forth, divided by 6. And so that should give us an answer of approximately 2.17. So 2.17, remember the units as well, meters per second squared. And that's all for now. So now what I want you to do is to try some of these yourselves to give yourself a practice and confidence with them. So if you want to turn to your Year 2 Stats and Mechanics books and head over to page 134 to 137. It's exercise 7b, and try all of the examination type questions labelled with a capital red E, and the problem solving ones too. Edexcel have done a brilliant job making these questions, so please do use them. So that's questions 5, 6, 7 and 8, then question 11 and question 12. So try all of those, assess your working regularly with the answers at the back of the book. If you get stuck, ask a neighbour or ask me in class, or even on the comment section in this video. Thank you for listening, please do subscribe, and I'll see you all soon. So, goodbye.